Greetings, my dear friends. Today, we lift our eyes to the sky, to where billions of stars twinkle, witnesses to the greatest story that can be told, the story of how the universe itself was born. Imagine silence, the absolute silence of night, when even the rustle of leaves seems loud. Now imagine a silence even deeper, a silence in which there is not only no sound, but also no space to spread it. There is no time to count the seconds of this silence. There is not even the concept of here and there. Tonight, you and I are going on a journey to the very beginning, to the point where not just history is born, but the very possibility of history itself. We'll talk about what scientists call the Big Bang, although, as you'll soon realize, it's one of the most unfortunate names in science. When I say the words Big Bang, what comes to your mind? Probably something like a giant bomb exploding in the darkness of space, scattering shards of matter in all directions. But no. Imagine you're inflating a balloon. On its surface are dots, galaxies. As the balloon expands, the dots move away from each other. But notice, there is no center of the explosion on the surface of the balloon. Each dot sees all the others moving away from it. This is exactly what is happening to our universe. It is not exploding in space. It is space itself, which is expanding. Every point in the universe can consider itself the center of this expansion. And this is not a poetic metaphor. It is a literal description of reality. Stop for a moment and think about it. Space itself is increasing in size. It is not objects moving through space. Space itself is stretching like a rubber film, and we are not on this film. We are woven from the very fabric of this space. The Big Bang Theory is not the story of how some bomb exploded 13.8 billion years ago. It is the story of how space, time, and matter itself began its existence from a state of unimaginable density and temperature. Imagine everything in the universe, every star, every planet, every atom in your body, compressed into a volume smaller than a pinhead. Now imagine that this volume, too, is still too much. What is density? In our everyday experience, we know that lead is denser than water, and water is denser than air. The densest substances we know are the nuclei of atoms. But even they are almost nothing compared to the density of matter in the first moments of the universe. Imagine the entire mass of Mount Everest compressed to the size of a pinhead. No, that's still not dense enough. Imagine the mass of the entire Earth in the volume of a grain of sand. It's still not dense enough. The mass of the sun in the volume of an atom. Closer, but not enough. But what is a beginning? Can we really talk about the first instant? This is where science gets painfully honest. The Big Bang Theory describes the evolution of the universe from the earliest moments we can understand, but not the first moment itself. It's like trying to describe the first breath of a newborn baby without knowing what conception is. There is something deeply humbling about this admission. Science, which has achieved so much, which has split the atom and sent man to the moon, is honestly saying, this is where our understanding ends. This is not defeat. It is wisdom. It is a recognition that reality is richer than any of our theories. So how do we know about this grand event? After all, none of us witnessed the birth of the universe, but the universe itself tells us its story. We just have to listen. And we have 4 main witnesses to this story. The first witness is fleeing galaxies. In 1929, astronomer Edwin Hubble made an observation that shook the foundations of our understanding of the cosmos. He noticed that galaxies are moving away from us, and the further away a galaxy is, the faster it runs away. It was one of those discoveries that change not just science, but the very way humans perceive their place in the universe. Imagine that you are standing on a railway platform, and trains are moving away from you in all directions. Moreover, the trains that are already further away from you are moving even faster. What would you think? It is possible that all the trains moved off one platform, yours, at the same time at some point in the past. That's exactly what's happening to galaxies. They are not running away from us because we are special. They are running away from each other. If we trace their movement back in time, we conclude that once upon a time, about 13.8 billion years ago, they were all in the same place. But how did Hubble figure it out? He used the Doppler effect, the same effect that makes the sound of an approaching train seem higher and the sound of a distant train seem lower. The light from distant galaxies becomes redder, shifts to the red part of the spectrum, and the faster the galaxy is moving away, the stronger this red shift. Hubble measured the distances to galaxies, an incredibly difficult task in itself, and compared them to their escape velocities. And he found a clear pattern. Velocity is proportional to distance. This became known as Hubble's law, and it was the first convincing argument in favor of an expanding universe. But think about the philosophical implications of this discovery. Before Hubble, we thought we lived in a static universe, eternal and unchanging. Stars might be born and die, but the very structure of the cosmos seemed constant. Hubble showed us that we live in a dynamic, evolving universe. The cosmos has a history. The second witness is even more startling. that we can literally hear the echo of the Big Bang, not with our ears, of course, but with our instruments. Imagine that in the distant past, a powerful chord was struck in a huge hall. The echo of that chord still fills the hall, although it has become very quiet. In 1964, two engineers, Arno Penzias and Robert Wilson, were working with a large radio antenna in New Jersey. They were trying to use it for satellite communications, but they encountered constant background noise. This noise was everywhere. Wherever they pointed the antenna, it remained. It didn't depend on the time of day, the time of year, the direction. It was a quiet, monotonous hissing sound that seemed to come from everywhere. At first, they thought the problem was with the equipment. They took the antenna apart, cleaned it, even removed the pigeon droppings that had accumulated inside. But the noise wouldn't go away. This persistent signal was wearing them down. Meanwhile, just a few dozen kilometers away, at Princeton University, physicist Robert Dicke and his colleagues were discussing a theoretical prediction. If the Big Bang really happened, there should be relic radiation left in the universe, the cooled light of the era when space first became transparent. It turned out that Penzias and Wilson had discovered this very radiation. The very noise that annoyed them so much was the voice of the Big Bang itself, coming through billions of years. This radiation fills the entire universe uniformly. Its temperature is just 2.73 degrees above absolute zero. It is the cooled light of the era when the universe first became transparent, about 380,000 years after it began. Until then, it was as hot and dense as the interior of a star, and light could not spread freely. Imagine the universe as a foggy day. When the fog is very dense, you can't see even a few meters away. Photons of light are constantly scattered on the water droplets in the fog. But when the fog clears, suddenly you can see for kilometers. That's exactly what happened to the early universe. When it cooled and expanded enough, the fog of free electrons and protons dissipated, hydrogen atoms formed, and light was able to travel freely. This moment is called recombination by physicists, and it is one of the most important moments in the history of the cosmos. It was then that the universe became transparent, and it is that light that we see today as relic radiation. But the most surprising thing is the small variations in the temperature of this radiation. Tiny fluctuations varying by tens of thousands of a degree. Modern satellites can map these fluctuations with incredible accuracy. And what they see is amazing. These tiny inhomogeneities are the seeds of future galaxies and stars. They are the very quantum fluctuations that existed in the primordial plasma and that gravity was able to amplify and transform into the structure of the modern universe. Each bright spot on the relic map is where a cluster of galaxies will someday form. Each dark spot is a future cosmic void. The third witness is the composition of the universe itself. About 75% of all ordinary matter is hydrogen, about 25% helium, and only a tiny fraction all the other elements. Where did this specific proportion come from? Georgy Gamow and his colleagues realized in the 1940s that in the first minutes after the Big Bang, the universe was a giant nuclear reactor. The temperature was so high, about 1 billion degrees, that protons and neutrons could overcome electrical repulsion and fuse to form the nuclei of light elements. But this window of opportunity was very short, only a few minutes. Imagine a baker who has to bake bread, but the oven is getting colder by the second. He has only a few minutes to cook the elements. In that time, deuterium can be created from a proton and a neutron, then tritium and helium-3, and then helium-4. But there is no more time to create the heavier elements. That would take stars and billions of years. This process is called primary nucleosynthesis, and its predictions match observations exactly. Everywhere we look in the universe, we find roughly the same ratio of hydrogen to helium. This is the universal signature of the Big Bang. Think about it. Every helium atom in a child's balloon was created in the first 4 minutes of the universe's existence. These nuclei survived 13.8 billion years of cosmic history to eventually end up in a toy in the hands of a child. The fourth witness is the architecture of the cosmos itself. Galaxies are not scattered randomly throughout the universe. If you look at their distribution on a large scale, you see a complex structure. Galaxies form filaments and walls separated by huge voids. It's like a cosmic spider's web, or the foam of soap bubbles. This structure emerged from the very tiny fluctuations we see in relic radiation. Gravity is a patient sculptor. It spent billions of years molding the universe we see today out of primordial irregularities. Every galaxy, every star is a descendant of that original quantum ripple in the fabric of space-time. Imagine how it happened. In areas where the density was just above average, gravity began to collect more matter. This made these areas even denser, which increased their gravitational pull. Over time, these small density excesses grew into galaxies and galaxy clusters, and the areas of lower density became increasingly empty. This process can be modeled on a computer. Start with a nearly homogeneous distribution of matter with tiny fluctuations. Add gravity and time, and see a structure emerge that is strikingly similar to what we observe in the real universe. But even such a slim theory has its mysteries. Imagine you are reading a detective novel, and suddenly you find a few pages that don't fit with the rest of the story. Doesn't that mean the whole novel is wrong? Not necessarily. Maybe you just need to better understand the motivations of the characters. The first problem is the singularity. When we trace the history of the universe backwards, the maths takes us to a point where density and temperature become infinite. But what does infinite density mean? This is the point where our physics just shrugs and says, "I don't know." This does not mean that the theory is wrong. It means that it is incomplete. Perhaps we need a new physics that unites quantum mechanics and gravity. Perhaps the very notion of beginnings needs to be reconsidered. A singularity is not a place in space. It is a state of space-time itself. Imagine the surface of a sphere. As you move towards the North Pole, the lines of longitude converge closer and closer. At the pole itself, the concept of longitude becomes meaningless. Perhaps a singularity is something like this for space-time. The second problem is even more subtle. It is the horizon problem. Relict radiation is remarkably uniform. Its temperature is the same in regions of the sky that are separated by vast distances, regions that could never communicate with each other if light is the fastest way to transmit information. It's like if you found two villages on different continents that had never been in contact, but the inhabitants all turned out to have exactly the same body temperature. How is that possible? How did different parts of the universe agree to have the same temperature if they could never exchange information? To understand the magnitude of this problem, imagine you are looking at relic radiation from two opposite sides of the sky. These regions are about 28 billion light-years apart. But the age of the universe is only 13.8 billion years old. Even light would not have traveled the distance between them in the entire time the universe has existed. Yet their temperatures match with an accuracy of 1 part in 100,000. The third problem is related to the geometry of space. Measurements show that the universe is remarkably flat. Its geometry is very close to Euclidean. In the general theory of relativity, this means that the average density of the universe is very close to the so-called critical density, but it requires incredibly fine-tuned initial conditions. Imagine trying to balance a pencil on a point. The slightest deviation in either direction, and it would fall. If the density was just above the critical density, the universe would quickly collapse. Anything less, and it would expand so fast that galaxies wouldn't be able to form. The fourth problem is a theoretical one. Many elementary particle theories predict that in the extreme conditions of the early universe, exotic particles called magnetic monopolies should have formed. These are particles that would have only one magnetic pole, either north or south only. Ordinary magnets always have a north pole and a south pole. Cut a magnet in half, and you get two magnets, each with its own north and south poles. But the theory predicts that particles with only one pole can exist. The problem is, we're not finding them. Where did they go? Finally, the fifth problem is the problem of baryonic asymmetry. According to our understanding of particle physics, the Big Bang must have produced equal amounts of matter and antimatter. When a particle meets its antiparticle, they annihilate, becoming pure energy. If matter and antimatter were equal, they would annihilate each other completely, leaving a universe filled only with radiation. But our universe is almost entirely matter. What happened to the antimatter? Where is it? Why did matter win in this cosmic battle? All of these problems seemed insoluble until an idea that was both simple and revolutionary emerged in the 1980s. Physicist Alan Guth proposed that in the very first moments of the universe's existence, between 10 to the power 36 and 10 to the power 32 seconds after the beginning, space was expanding not just fast, but exponentially fast. This is called cosmic inflation. To understand what it means, imagine a region smaller than a proton inflated to the size of a grapefruit in a time that is trillions of times shorter than it takes light to cross a proton. Sound impossible? But this idea elegantly solves all our problems. Inflation is not ordinary expansion. In ordinary expansion, if you double time, the size doubles. In inflationary expansion, the size grows exponentially. Doubling time can increase the size trillions of times. Imagine you have a piece of paper that is a millimeter thick. Fold it in half and it becomes 2 millimeters thick. Fold it again, 4 millimeters. That's linear growth. But if the thickness doubles every second by itself, then in 10 seconds, the sheet will be more than a meter thick. In 20 seconds, it will be more than a kilometer thick. In 30 seconds, it will be more than the distance to the moon. That's how inflation works. In a tiny fraction of a second, space can grow by fantastic proportions. And this idea solves all our problems in one elegant stroke. Horizon problem? Solved. The various parts of the observable universe were once a tiny region, smaller than a proton, that had time to come to thermal equilibrium before inflation. Inflation then bloated that region to its observable size. This is why different parts of the sky have the same temperature. They were once in contact. Flatness problem? Solved. Any curvature of space has been stretched by inflation to the point of indistinguishability, like wrinkles on a balloon become invisible if you inflate it too much. After long enough inflation, any universe will become flat. The magnetic monopole problem? Solved. They have been diluted by inflation to the point where the probability of finding one in the observable universe is virtually zero. They may exist, but they are so rare that we will never encounter them. But inflation is not just a convenient hypothesis invented to solve problems. It makes specific predictions about what fluctuations in relic radiation should look like, and these predictions are confirmed by observations with remarkable accuracy. Moreover, inflation predicts that fluctuations should have a certain statistical structure. They should be Gaussian, meaning that large fluctuations should be less frequent than small ones in a strictly defined proportion. And this is exactly what we observe. Inflation also predicts that fluctuations should be almost, but not quite, scale invariant. This means that fluctuations on large scales should be slightly weaker than on small scales. Again, this is exactly what the measurements show. But what caused the inflation? Here we enter an area where the theory becomes more speculative. Most inflation models assume the existence of a special field, the inflaton field, that filled space in the early universe. This field had a special property. Its energy was not dilute as space expands. Usually, when space expands, the energy density drops. The same energy is distributed over a larger volume. But the inflaton field behaved differently. Its energy density remained constant, which caused exponential expansion. Eventually, the inflaton field decayed, transferring its energy to ordinary particles and radiation. This moment is considered to be the end of inflation and the beginning of the hot Big Bang, the period described by the Standard Theory. And here we come to the most exciting question. What was there before the Big Bang? This question has plagued mankind ever since we realized that the universe had a beginning. Science gives a remarkably honest answer. We don't know. Moreover, the question itself may be meaningless. Time, as we understand it, may have begun with the Big Bang. Asking what was before time is like asking what is north of the North Pole. St. Augustine, in the 4th century AD, already understood this problem. When he was asked what God was doing before the creation of the world, he replied, "Time itself was created by God, so before the creation of the world, there was no time." Modern physics has come to a similar conclusion, albeit in a different way. Space and time are inextricably linked into a single fabric of space-time. If this fabric began with the Big Bang, then the question, what was before, loses its meaning. But there are more intriguing possibilities. Our universe may have arisen from quantum fluctuations in the vacuum. But this is no ordinary vacuum, a void with nothing in it. The quantum vacuum is full of virtual particles that constantly appear and disappear. In quantum mechanics, The Heisenberg uncertainty principle allows energy to be borrowed from the vacuum for a very short time. The more energy is borrowed, the shorter time for which it is possible. Usually, these fluctuations are microscopic and imperceptible, but perhaps one of these fluctuations was so powerful that it spawned an entire universe. It sounds incredible, but in the quantum world, incredible things happen all the time. They just usually happen on microscopic scales. There is another beautiful idea, the zero-energy universe hypothesis. All positive energy of matter can be exactly compensated by negative gravitational energy. The total energy account is zero. And to create such a universe, it is not necessary to violate the law of conservation of energy. Imagine you are digging a hole. The earth from the hole forms a hill next to it. If the pit has volume 5 and depth h, the hill has the same volume v and height h. The total change in height is 0. You didn't create or destroy the earth, just redistribute it. Perhaps the universe works in a similar way. Matter is the hill, and the gravitational field is the pit, and in sum, everything is 0. But the Big Bang Theory is not the only possible history of the universe. There are other ideas, each offering a different view of the nature of reality. One alternative is the idea of a stationary universe. Fred Hoyle, who incidentally coined the term Big Bang in mockery during a BBC radio program in 1949, suggested that the universe has always been as it is now. Yes, it is expanding, but new matter is constantly being created from nothing to maintain a constant density. Imagine an escalator going downhill. The people on it represent galaxies. As the escalator moves, people move away from each other. This is expansion. But at the same time, new people are constantly entering the escalator from above, so that the total density of people remains constant. This idea is beautiful in its simplicity. It avoids the problem of the beginning. In a stationary universe, there is no moment of creation, no singularity, no need to explain what was before. The universe has simply always existed in the same form. Hoyle and his colleagues developed a detailed mathematical model of such a universe. They called it the theory of continuous creation. According to their calculations, to maintain a constant density in an expanding universe, only one hydrogen atom per cubic meter of space would need to be created every billion years. This is so small that it would be impossible to detect such a creation. But observations, especially the discovery of relic radiation, left this theory no chance. The stationary model could not explain where this radiation came from. The discovery of Penzias and Wilson was a death sentence for Hoyle's theory. Interestingly, Hoyle himself remained a skeptic of the Big Bang Theory to the end of his life. He continued to develop alternative models, trying to find a way to explain the observations, without involving the idea of the beginning of the universe. This shows how important it is in science to have skeptics. They force the proponents of the dominant theories to constantly test and refine their models. Another intriguing idea is a cyclic universe. Perhaps our universe goes through endless cycles of expansion and contraction. The Big Bang is followed by a big contraction, then another Big Bang, and so on ad infinitum. Imagine the breathing of a giant creature. Breathing in is expansion. Breathing out is contraction. And so, billions of cycles, each lasting tens of billions of years. We are living in the inhalation phase of one of these cycles. This model solves the problem of the beginning. If the cycles are infinite, there is simply no beginning. It could also solve the entropy problem. According to the second law of thermodynamics, entropy, a measure of disorder, should be constantly increasing. Eventually, the universe must reach a state of maximum entropy, when no more change can occur. But in the cyclic model, each contraction could reset entropy, returning the universe to a low entropy state, ready for a new cycle of development. It is as if a giant washing machine periodically washes the universe, returning it to its original state. However, the cyclic model has serious problems. It is not clear how the transition from contraction to expansion can take place. What stops the collapse and starts a new expansion? And what happens to information? Is something passed from cycle to cycle? Or does each cycle start with a clean slate? Current observations show that the expansion of the universe is accelerating, making compression unlikely. But some physicists continue to work on cyclic models, trying to find mechanisms that could bring them about. Perhaps the most dizzying idea of all is the multiverse. What if our universe is just one of an infinite number of universes, each with its own laws of physics, its own constants, its own history? Inflation can create such a multiverse. If inflation is not a one-time event, but a constant process, it can generate an infinite number of pocket universes, each of which will have its own history. Imagine a boiling pot of water. Each bubble of vapor is a separate universe. Bubbles are constantly forming, growing, separating from the main mass of water. Each bubble is its own world with its own laws. In such a multiverse, inflation never ends globally. It ends locally, in separate areas, creating pocket universes like ours. But in general, the process continues forever, constantly creating new worlds. In some of these universes, the constants of nature may be quite different. Gravity may be stronger in one, weaker in another. An electron may be heavier in one, lighter in another. Most of these universes will be empty and lifeless. But among the infinite number of them, there will be some where everything will work out well for the existence of matter, stars, and life. In such a multiverse, the problem of fine-tuning is solved elegantly. There is no need to explain why the constants in our universe are ideal for the existence of life. Among an infinite number of universes, there is bound to be one where everything worked out well. And we observe just such a universe simply because we could not exist in others. This is an application of the anthropic principle, the idea that we observe precisely those properties of the universe that are compatible with our existence. Not because the universe has been specially configured for us, but because we can only exist in those universes that allow our existence. But the multiverse is not just a solution to the problem of fine-tuning. It is a radically new way of looking at the nature of reality. If it exists, much of reality will forever be inaccessible to us. We will never be able to directly observe other universes or communicate with them. This raises profound philosophical questions. Can a theory that is fundamentally unverifiable be considered scientific? Does it make sense to talk about the existence of something that cannot be observed, even in principle? Some physicists see the multiverse as a natural consequence of our best theories. Others criticize it as a departure from the scientific method. The debate continues, and it is unclear how it will be resolved. But what does the future hold for our universe? This is a question that concerns each of us, although the answer lies in the distant future, so distant that the human mind can barely comprehend it. The future of the universe depends on several key factors. The first is the average density of matter. If the density is less than the critical density, the universe will expand forever. Galaxies will move away from each other faster and faster. Stars will gradually burn out, and the universe will slowly cool down to absolute zero. This is called the heat death of the universe, the state of maximum entropy, when no more changes can occur. All stars will go out. All black holes will vaporize through the Hawking radiation process, and only the rarefied gas of elementary particles in infinitely expanding space will remain. But how long will it take? The numbers are dizzying. The last stars, red dwarfs, will shine for trillions more years. The most massive black holes will take 100 years to vaporize. This number is so large that the human language has no words to describe it. By comparison, our universe is only 13.8 billion years old, which is about 10 years. If the density is greater than the critical density, the expansion will someday stop, and the universe will begin to contract. Galaxies will converge, collide, merge. temperatures will rise, stars will explode from overheating. Eventually, everything will collapse into the Big Bang, the mirror image of the Big Bang. This scenario is called the Big Crunch. Time will flow like a film playing backwards. First galaxies will merge, then stars, then atoms will collapse into elementary particles, and finally, everything will collapse into a singularity. But modern observations show something completely unexpected. The expansion of the universe is not slowing down, it is accelerating. This discovery, made in 1998 by two independent groups of astronomers, has become one of the most important in modern cosmology. The culprit is a mysterious dark energy that makes up about 70% of the universe's energy. We don't know what it is. It could be the energy of space itself, the so-called cosmological constant, which Einstein introduced into his equations. Or it could be something more exotic, a scalar field similar to the one that caused inflation. Dark energy behaves very strangely. Unlike ordinary matter, whose density falls as the universe expands, the density of dark energy remains constant. That means that the bigger the universe gets, the more dark energy there is. And this energy works like anti-gravity, speeding up the expansion. If dark energy remains constant, the universe will expand at an accelerating rate forever. But there is a more dramatic scenario: the Big Rip. If the density of dark energy grows with time, it will eventually become so strong that it will tear apart not only galaxies and stars, but also atoms and even space-time itself. Imagine that you are stretching the rubber band faster and faster. At some point, it will fail and tear. The same can happen to the fabric of space-time if the dark energy grows unlimitedly. According to some calculations, if this scenario is correct, the Big Rip will occur in about 22 billion years. First, the ties between galaxies will break, then between stars in galaxies, then between planets and stars, then molecular bonds, then atomic bonds, and finally, space-time itself will break apart. There are other exotic scenarios. Big Bounce suggests that the universe shrinks to an incredibly small but finite point and then bounces back, returning to a new Big Bang state. This could unify the ideas of the Big Bang and the cyclic universe. Some theories predict the decay of the proton, the most stable known particle. If protons do decay, in the distant future, there won't even be any atoms left. The universe will be filled with only the lightest particles, electrons, positrons, neutrinos, and photons. But whatever the fate of the universe as a whole, we know what awaits our own cosmic neighborhood. In a few billion years' time, our Milky Way galaxy will collide with our neighboring Andromeda galaxy. It will be a grand collision of two giant star systems. But don't worry, it will be a very mild collision. The stars are so far apart that the chances of a direct collision are negligible. The two galaxies will just dance through each other. And then gravity will force them to merge into one big elliptical galaxy. What will happen to our sun? It will continue to shine for about 5 billion more years, gradually getting brighter and hotter. At some point, the Earth will become too hot for liquid water to exist. The oceans will evaporate, and our planet will become a lifeless desert, like modern Venus. Eventually, the sun will run out of hydrogen fuel in its core and start burning helium. It will swell to the size of a red giant, possibly swallowing Mercury and Venus. Earth may survive on the edge of the expanding solar atmosphere, but it will be a scorched ball of rock. The sun will then shed its outer layers, forming a beautiful planetary nebula, and its core will shrink into a white dwarf, a hot, dense star about the size of Earth. The white dwarf will slowly cool down over trillions of years until it becomes a cold black dwarf. But that's all in the distant future. What's happening now? How does all this change our understanding of ourselves? The Big Bang Theory doesn't just tell us about the origin of the universe. It gives us a whole new perspective on our place in the cosmos. We are not just observers of the universe. We are its product. Every atom in our bodies was created in the core of a dying star or in the first minutes after the Big Bang. We are literally made of stardust. The iron in our blood, the calcium in our bones, the carbon in our genes, all of this was forged in stellar furnaces billions of years ago. Think about it. The iron atom in your blood was once part of a star that lived and died long before the sun was born. That star collected light elements, hydrogen and helium, and fused them into heavier elements in its core: carbon, oxygen, neon, magnesium, silicon, sulfur, and finally iron. When the star ran out of nuclear fuel, it exploded as a supernova, scattering all those elements across the cosmos. The shock wave from the explosion compressed nearby clouds of gas and dust, triggering the formation of new stars, including our sun. The carbon atoms in your body remember the interior of dying stars. Oxygen atoms remember the cosmic cold of interstellar space. Hydrogen atoms remember the first minutes of the universe, when the temperature was 1 billion times higher than at the center of the sun. And we are not just passive products of cosmic evolution. We are the way the universe knows itself. Through our eyes, the universe looks at itself in the mirror. Through our minds, it tries to understand its own nature. Through our telescopes, it looks into its own past. When you look at the stars, you see the past. Light from the nearest star took 4 years to reach you. Light from the center of our galaxy is 26,000 years. Light from the neighboring Andromeda galaxy, 2.5 million years. And relic radiation carries information about what the universe looked like 13.8 billion years ago. This means that astronomy is the only science that can study the past directly. Geologists reconstruct Earth's history from fossils and rocks. But astronomers see cosmic history through their own eyes, or rather, through the eyes of their instruments. Perhaps that's the most amazing thing about the Big Bang Theory. It shows that we are not strangers in this world. We are not random aliens in an indifferent universe. We are a natural consequence of the same laws that created the stars and galaxies. The gravity that assembled the first stars from hydrogen and helium is the same gravity that holds us together on Earth. The nuclear forces that fuse hydrogen into helium at the center of the sun, the same forces that hold together the atoms in our bodies. The electromagnetism that makes stars shine is the same electromagnetism that allows our neurons to transmit signals. We are made of the same elements as the stars. We obey the same laws of physics. We participate in the same cosmic evolution. In a sense, the universe has evolved consciousness to understand itself, but there is a deeper level of connection. The very quantum fluctuations that created inhomogeneities in the early universe and eventually led to the formation of galaxies and stars may also have laid the foundations for the evolution of complexity, from simple molecules to life, from life to intelligence. Perhaps the appearance of consciousness in the universe is not an accident, but an inevitable consequence of physical laws. Perhaps the universe from the very beginning carried in itself the potential to know itself. This raises one of the deepest questions we can ask. Why does something exist and not nothing? Why are the laws of physics exactly what they are and not others? Why do the constants of nature have the values they do? One of the most puzzling features of our universe is what physicists call the problem of fine-tuning. The fundamental constants of nature, the gravitational force, the electromagnetic interaction, the masses of elementary particles, all have values that seem perfectly matched for the existence of complex matter and life. Change the gravitational force by a fraction of a percent, and stars will not be able to form or will burn out too quickly. Change the mass of an electron, and atoms become unstable. Change the strength of the strong nuclear interaction, and stars will not synthesize elements heavier than hydrogen. The cosmological constant, the energy of empty space, is also remarkably fine-tuned. If it were slightly larger, the universe would expand so fast that galaxies would not be able to form. If it were negative and modulo large, the universe would collapse before stars could form. Some see this as evidence of intelligent design, the idea that the universe was specifically designed for life to exist. Others explain it by the anthropic principle. We observe this universe because we could not exist in another. The anthropic principle has weak and strong forms. The weak anthropic principle simply states a fact. We observe those properties of the universe that are compatible with our existence. This is a tautology, but a useful tautology. It reminds us that our existence places constraints on what properties of the universe we can observe. The strong anthropic principle goes further. It asserts that the universe must have properties that allow intelligent life to evolve. This is a more controversial claim that borders on teleology, the idea of purposefulness in nature. The third explanation is related to the multiverse. If there are an infinite number of universes with different constants, then among them there are bound to be those where everything turned out to be lucky for life. We live in one of such lucky universes, not because it was specially set up, but because it is the only type of universe in which we can exist. But perhaps there is a fourth explanation. Perhaps the constants are not independent, but are bound by underlying laws that we do not yet understand. Perhaps there is only one way to create a stable, long-lived universe, and we live in the only possible world. Some physicists are looking for a theory of everything, a single theory that would unify all fundamental interactions and explain why the constants of nature have the values they do. Such a theory could show that fine-tuning is not an amazing coincidence, but an inevitable consequence of underlying principles. String theory is one candidate for such a theory. It assumes that all elementary particles are different ways of vibrating tiny one-dimensional objects called strings. In some versions of string theory, the constants of nature are determined by the geometry of extra dimensions of space. But string theory faces a problem. It predicts a huge number of possible vacuum states, perhaps 10^500 or more. Each such state corresponds to a universe with different laws of physics. This is called the landscape of string theory. If the landscape is real, we come again to the idea of the multiverse. Different regions of the multiverse can correspond to different points in the landscape, each with its own constants and laws. Again, we observe those constants that are compatible with our existence. The problem of fine-tuning remains one of the deepest mysteries of modern physics and cosmology. It concerns the most fundamental questions about the nature of reality and our place in it. The Big Bang Theory is one of the greatest achievements of the human mind. It explains the origin and evolution of the universe, gives us an understanding of our place in the cosmos, and predicts the future of the universe. It shows how the universe, full of stars, planets, and life, grew out of quantum fluctuations in the primordial vacuum. But it also shows us the limits of our knowledge. We don't know what caused the Big Bang. We don't know what dark matter and dark energy are, which make up 95% of the universe. We don't know if there are other universes. We don't know why the constants of nature have the values they do. We don't know if intelligent life will appear somewhere else in the universe. And there's a beauty in that. Science doesn't kill the mystery. It deepens it. Every answer raises new questions. Every discovery opens new horizons of ignorance. We stand on the shore of an infinite ocean of knowledge, and each wave that reaches us shows how deep this ocean is. We live in a remarkable time. For the first time in human history, we can tell a coherent story of the universe from the first moments to today. We can look billions of years into the past and see how the first stars were born. We can predict the future trillions of years into the future and understand the fate of the cosmos. But most importantly, we can wonder. To wonder that from a quantum ripple in the primordial vacuum grew a universe full of stars and planets. We can marvel that from simple hydrogen and helium atoms, evolution was able to create us, beings capable of asking questions about our origins. The Big Bang Theory is not just a scientific theory. It is a new creation myth based on observation and experimentation. It's the story of how everything came from almost nothing. It is the story of our cosmic home and how we got there. And that story continues. Every night, when you look up at the stars, you see a continuation of that story that began 13.8 billion years ago. Every breath you take is part of that same story. Every thought you have is the way the universe reflects on itself. We are all children of stars, born out of a big bang that wasn't an explosion. We are all part of the greatest story ever told, and that story is far from over. Think about it as you close your eyes. Your body is filled with blood containing iron that was born in the heart of a dying star billions of years ago. Your lungs are filled with oxygen forged in thermonuclear furnaces long before the sun. Every cell in your body holds carbon that remembers the cosmic cold of interstellar dust. You are not just living in the universe. You are the universe, which has become aware of itself. Through your eyes, the cosmos looks at its reflection in the mirror of time. Through your thoughts, it tries to understand its own nature. Now imagine falling asleep not in your room, but in the heart of a cosmic story. Your bed is a small planet drifting in the vast ocean of space-time. Above you is not a ceiling, but an infinity dotted with billions of suns. Each star you see is a whole world, with its own history, its own planets, perhaps its own life. Some of these stars are older than our sun, remembering a time when Earth did not yet exist. Others are young, newly lit, and their light has not yet had time to reach us. Somewhere in this infinity, new worlds are now being born. Gravity is slowly gathering cosmic dust into clumps that will become planets. Somewhere supernovae are exploding, seeding space with heavy elements, the future building blocks of life. And somewhere, perhaps, other beings are also looking up at the stars and asking the same questions we are. They too are pondering where their universe came from, how it works, whether they are alone in the cosmos. And perhaps their thoughts, like ours, are the way the universe knows itself in the silence of the night, as sleep begins to envelop your consciousness. Allow yourself to feel this deep connection. You are not separate from the cosmos. You are part of it. Your dreams are dreams of the universe itself. Your dreams of distant worlds are the cosmos' memory of its past and a premonition of the future. And may you dream of space. May you dream that you are floating between the stars, feeling space-time gently bending under the weight of galaxies. May you dream the first light broke free 13.8 billion years ago and is still traveling through the universe. May you dream of distant worlds where other life forms gaze up at the same stars we do. May you dream that you are a quantum fluctuation, which once accidentally appeared in the primary vacuum and grew into a whole universe of thoughts and feelings. May you dream that you are a quantum fluctuation that once appeared by chance in the primary vacuum and grew into a whole universe of thoughts and feelings. And may you dream of the moment when the universe first opened its eyes and saw itself. The moment when somewhere in the cosmos the first consciousness appeared, capable of asking the question, where did I come from? Perhaps that first consciousness was you. Sleep well, child of the stars. Your dreams are the dreams of the cosmos, and the cosmos dreams of the day when all its mysteries will be solved, all its stories told, and the universe will finally understand itself completely. See you in the world of dreams, where time flows back to the very beginning and space opens up like a flower, revealing all its hidden dimensions.